Hey folks, how y'all doing? On Friday we started section on coding graph algorithms. We're going to finish that up today. Before we mention that, let me mention on the course website. I have a makeup policy up there for missed classes. We're getting at a point in the semester where a lot of people are quarantining, and that's understandable. But um, the content of the course is about to get a little bit more difficult, and I want to make sure that people are not falling behind. And so, if you're in any of the CRNs that have hybrid sections, um, check out this policy. If you are in the section, the remote section, you're encouraged to make use of my online office hours over the next few weeks. But we're going to be writing some code coming up soon, and this is the second day on that. So let's go ahead and get started. Um, so, what I want to do here, this is a very simple weighted graph, and we goal is to find the minimum weight spanning tree. So goal is to find the minimum weight spanning tree. Um, but I wanted to sort of talk about how we would do this using Kruskal's algorithm, but I'm going to do a little bit more detail in how I'm going to talk about how we would implement this. Um, First thing I'm going to do is I'm going to sort the edges by weight. So my smallest edge by weight is AB, then AC, then DE, then BC, then CE, and then finally BD. And these have weights 1, 2, 3, 4, 5, and 6. And what I'm going to do is I'm going to have two lists over here. I'm going to have a list of components. I'm going to have a list of the edges that are actually going to be in the spanning tree. Okay. So I go through this queue, and what I want to do is I want to check is A or B in my list of components. And since the answer is no, neither one of them is in there, a couple of things I'm going to do is I'm going to go ahead and add the edge AB to my spanning tree. Um, and I'm going to create a component that contains A and B. So what I'm saying is that the spanning tree is going to contain these edges, and they form a component because they're connected together. Okay. So now I'm going to go through this process with AC. Is A or C in my list of components? And the answer is A is, but C isn't. Um, so what I'm going to do is go ahead and add this to the edge to the spanning tree. So AC with a weight of 2 gets added. And since A is in there but not C, that tells me that C is going to connect to the same component with A. So we're going to add C to the component containing A. So what that's going to mean is that, this component now contains A and B and C. All right. So now let's go through the next edge on the list. DE. Is D or E in my list of components? And the answer is neither one of them is. I'm abbreviating this, but my list of components. Neither one is. So I'm going to go ahead and add DE to my spanning tree and create a new component containing D and E. Add to spanning tree. And put D and E in a new component. And so now I have a new component containing D and E. So now I have, what I'm remembering is that my spanning tree will contain all 3 of these edges, and these vertices A, B, and C are all connected together, and then vertices D and E are all connected together. All right. So now I go through BC and see is B or C in my list. And in fact, they are, and they're in the same component. Yes. And they're in the same component. And that tells me if I were to put an edge from B to C, then they would be connected in a cycle. Being in the same component means I can already walk from B to C. Putting the edge from B to C would turn that walk into a circuit. And so we do not add this edge. So we go to the next edge, CE. Is C or E in my list? And the answer is yes, but they're in different components. And so I'm going to add CE to my spanning tree that has a weight of 5. Go. And I'm going to merge these components together now. That C and E used to be in separate components. They are now in a single component all by together. All right. Now, at this point, we have a spanning tree, but I'm going to go ahead and complete the queue. Is B or D in my list? And the answer is yes, and they are now in the same component. So we do the same thing we did up here. We do not add them to this edge. Yes, in the same component. So we do not add. And so we have one component that contains all 5 vertices. That's good. And our spanning tree contains these 4 edges. Okay. That's just a review of how Crucicles works. So let's now talk about how we're going to implement this. First of all, we're going to have to be able to read in the graph from a file. For our purposes, we're going to store the graph in a CSV file with the first value in the list of common separated values is how many vertices. And then from that point on, the remaining entries form an adjacency matrix. So this is a valid input file. The first number says we have 10 vertices. And then the next 10 numbers, 3, 4, 5, 6, 7, 8, 9, 10, would be the top row of an adjacency matrix. It tells me that the first vertex doesn't connect to itself. It doesn't connect, so the first vertex, if we call it vertex 0, doesn't connect to itself or to vertex 1, but it connects to all of the other vertices, and the weight from vertex 0 to vertex 8 is 4. That would be the cheapest route out of vertex 0, if that makes any sense. And then the next 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 entries would be row 1 of the adjacency matrix, and so on and so forth. Okay? So here's some code that will do this. Python has a built-in routine for working with CSV files. We're going to go ahead and open this file as a CSV file. We're going to give the file a handle and say we're reading this. The R here stands for read-only mode. So we won't accidentally overwrite the file. And then the data, this just grabs the first line of the file. But if we don't put any line breaks at the end of these lines, if we just treat this as just one line of text, it will read the whole file. So this reads the whole file. And then we're going to initialize some lists. The number of vertices will be the first number in the list, which is numbered 0, because anyway, the first entry in the list is data 0, not data 1, which we're going to convert to an integer. It already is an integer, but it's being stored right now as text. So we convert that to an integer, make that the number of vertices. This next line is cut off on this slide, but I've got the source code where you can look through it. It's going to set, it's going to create a graph of all zeros, that the rows are going to go from I up to the number of vertices, and the rows are also going to come from J up to the number of vertices. And then we start with an empty list of edges. So there are not any edges in the spanning tree yet. And we're initializing integer k equal to 0, which we're going to use in just a moment. Okay? All right. So what we're going to do now is loop through the number of vertices for the rows and for the columns of the matrix. We're going to place in the ij position the kth data value, where k gets incremented every time we go through this. And if the value of the kth data value, and in both times we're going to have to convert this to an integer. If it's not 0, if this is not equal, the little exclamation part makes it not equal. If this makes this not equal to 0, that means there is an edge and it has some weight. We're going to add to our list of edges an edge that has the weight first, and then the starting vertex, and the ending vertex. By placing the weight first, then when I do this sort command at the end that sorts the edges, it sorts automatically by weight, because weight is the first thing in the list, and I don't have to be fancy about how I'm sorting. Okay? So that's how that works. The next couple of slides sort of annotates what we've done. CSV stands for comma separated values. Python has a built-in library for reading these files. We're going to read a single line of data, and the first element is numbered 0 in the list. So we have to use int to convert them to numeric values. We are building an adjacency matrix and a list of edges, but then here we read all of the information and put them back into a matrix. That's what we want to do. Okay? Placing the weight first makes it easy to sort the list. All right, so now we have this information in our file. We have a table of all of the edges and the adjacency matrix being stored. So we have this list that's stored. We want to process that, but we want to not add all of the edges in the list. We want to add all the edges that don't create a cycle. So how do we tell if an edge creates a cycle? We're going to keep not only a list of the edges that are in the spanning tree, but we're also going to keep a list of components. This is what we did in the example at the beginning of the video. So for all of the edges in our list, we have a whole long list of edges. For every single edge in that list, the start vertex is edge 1 and the end vertex is edge 0. And remember that the weight we put at the beginning, which is edge 0. But we're not going to have to use the weight here. We're just checking to see if the edges are in the same component or different components. Initially, we're going to set the start and end component to be the null value. In Python, the null value is the word none. But in other cases, we might want to use, some null value. Right now, these don't have components that are defined yet. All right, so what we're going to do next is go through all of the components. If the start vertex is in one of the components, then we're going to update the start component so that it's not null anymore. It will be whatever component we find. And if the end vertex is in a component, we're going to update the end component and set it equal to whatever component we find there. So that's what happens here. We're going through all of the components and checking if the start vertex and end vertex is in that list. All right. So let's look at a couple of things here. If the start component doesn't equal none, in other words, we have a start component and it's the same as the end component, then this edge is going to create a cycle that what component we're starting in and what component we're ending in are equal. So if this happens, we do not add the edge because it will create a cycle. Okay. All right. If both components are none, that means neither vertex has been used. And so we create a brand new component containing both of those edges. And so we're going to add a new component containing those endpoints. We're going to append to the list of components a list containing the start vertex and the end vertex. And we're going to append the edge to the spanning tree because we are going to go ahead and keep the edge in this case. All right, the next two cases are very similar. If I find the start component but not the end component, what we're doing there is if I find the start component but I don't find the end component, I am adding this vertex onto an existing component but not creating a new component. So we'll go ahead and reuse K because we're done with the routine that we used K for. We're going to let that be the index of the end component. And then for that index, components at that index, we're going to append the start vertex of that list. So we're adding the start vertex to this component. And then since we are definitely going to use that edge as part of the spanning tree, we add that edge. We append the edge to the spanning tree. This is the same logic, just what happens if the end component is null and the start component is not. So we have both cases up here. All right. The last case is what happens if we have vertices that are in different components? So the start component is not the null component. The end component is not the null component. And again, this is cut off, but the start component and the end component do not equal each other. They are not equal. Then we know that we have vertices that are in different components, so we have to merge them. So we find the index of the start component, and then we go through all the vertices in the end component and take the component at position K and append that vertex to the list. Now, this may end up resulting in a vertex being duplicated. That, vertex number 4 may be in the index of the start component and in the end component. That may happen, but it should not happen, because that would mean that everything in the start component could walk to 4 and everything in the end component could walk to 4, but that would make them one component. So, like I said, this will work even if we have some duplicated vertices, but duplicated vertices literally should never happen. Okay. Once we have appended all of the vertices into the main component, then we're going to remove the end component and delete that from the list. We print a message saying that we're merging these, and then we append that edge to the spanning tree. Okay, so on line 22, we're looping through every edge in the graph. Python uses indentation to indicate the extent of a loop, so this loop extends all the way down to line 65. We read the start and end vertex and set their components to none, which is an undefined value. It's what most other languages call null. And then we go through each component to see if the starter vertex is found in that component. This is a little complicated because, well, it's not really. We have to go through the list of components. We have to check to see if the start vertex is in the component, and then we check to see if the end vertex is in the component. And if they are, then we're going to set these values so that they're not the null value. All right. And then we look at all the different possible outcomes. There are a lot of cases here that the start component and the end component are both null. One of them's null, but the other one isn't. Or this one's null and this one isn't. Or neither one is null, but they are different components. Or neither one's null and they're the same component. So we have all 5 cases we have to check. But what to do in these cases should be pretty straightforward. The only really complicated one is the case where the start and end vertex are in different components. So I have one component over here, I have one component here, and I want to add the edge that will join them together. Then what we have to do is we have to take these 2 vertices and add them to this component, and then this component will include all of these vertices. And then we have to delete the component that contained those vertices a second time. Okay. So now we've done the cycle detection, and we have exhausted all of those lists of edges. So now what we want to do is print the edges that ended up into the spanning tree, but we'd like to reformat them a little bit, because for sorting purposes, we put the weight first. What we like maybe to do is show the vertices first. And so for each edge in the spanning tree, I'm listing them, from this edge to this edge. So with a little hyphen between them. So we'll get like edge, well, it's capitalized, edge 3-6 would be the edge from vertex 3 to vertex 6 with weight And hopefully the weight isn't too bad, but we'll say with weight 3, for example. And then it's pulling the weight from the front of the list. Okay. So short routine to print the output, much longer to routine to do the cycle detection. And the file input is pretty straightforward if you've done this sort of thing before. Okay. If you have any questions about this code, come by my office hours, ask about it. On Wednesday, we will go ahead and release the first coding project. We will use Wednesday's class to go over the algorithm in a video, and then you'll write some code for it. Okay? You take care. See you around.